This one, we're going to start with LED lighting terminology. Terminology is one of the things that is the most forgotten part of anything, you know. So before we go on, we must understand the terms that sit behind any and all electronic componentry and why it exists. Terminology is one thing that basically stifles and confuses so many people. So the aim of the fact sheet is to give you that information so you don't have to, you can look more professional and sound more professional when you're talking with your customers. So as I said, all the information is in here. There is also a PowerPoint presentation that you can actually refer to as well. What is terminology? Well, here we go. In most cases, terminology is based around a product or a service, and it's a way of describing an action, a function, or an outcome. Not to be confused with an acronym, that's a little bit different, which is something that just shortens a word or a phrase, or a group of a phrase, or a letter, sorry, or a group of letters. For example, LED is a light emitting diode. LED is the acronym. Okay, why is terminology important? Basic terminology is extremely important, as in most instances it will be attached as an indicator which will relate to an output, an efficiency, a safety factor, a quality, or similar. Without terminology, the numbers would mean very, very little, and it would be difficult to describe or reference the product that you're looking for. All right, so this is why we need terminology. Let's start with something really simple. Various LED chips and terms. Okay, LED, we just went through that one. It's a light emitting diode. It's an electronic component like resistors, capacitors, etc. It is made of semiconductor material. We all know what it is from there. Okay, it emits light. But based on the construction, we have available LEDs that are classified as dual inline package, surface mounted diodes, chips on board, and multiple chips on board, all of which have a place in society. A dual inline package, what's that? Well, let's have a look. This is a little bit hard to see, but what you can see is they are the old style indicator style G LEDs. Okay, so based on that, when we say a dual inline package, what we're looking at is we have our anode and our cathode. They go up through the top, and this is explained a little bit further in a few diagrams, but everything's in line. Whereas with a surface mounted diode, everything's flat and laid out. Okay, which is more efficient? The surface mounted diode is more efficient. The chip on board is used in traffic lights, torches, things like that. But they all have a place. They all have a place in society. But the dual inline package is a small, used for indicators and things like that, indicator lights and things like that on switchboards, control boards and things like that. Surface mounted diode is a chip which consists of single or multiple LEDs mounted on a surface of a particular size. Your classic surface mounted diode is on your LED strip. Okay, they're surface mounted diodes. The LED strip is a printed circuit board. The diode is attached directly to the printed circuit board. That's a single colour. You can get multiple colour. You can get RGB, RGBW, RGBWW, and so on and so forth. That's a surface mounted diode, and it is efficient because of its design. Chips on board, a combination of multiple diodes, usually 9 or more, with only 2 pins. So when we look at a chip on board, if we were to say that's a chip on board, one diode, there would be 9 small diodes inside that. Okay, and it would have only 2 pins. So you can't control those 9 diodes individually, you can only control them as one. So that's chips on board. And multiple chips on board are multiple chips on board collectively all in one to do one function. Okay, so just remember that. All right, dimming. as I said, this is the general knowledge, the overview. So we do skip around a little bit, but dimmers are devices which are connected to a light fixture and used to lower the brightness of the light. As simple as that. But all dimmers are not the same. Let's be clear on that, because everyone seems to think, oh, I just want to dim a light, so I'm just going to go and get a rotary dimmer from Bunnings. All dimmers are not the same. You have leading edge, you have trailing edge, you have Dali, you have 0 to 10 volt, you have KNX, they just go on. You've got push dim, you've got Zigbee, Z-Wave, Philips Hue, Google's. All of those can act as dimmers. Okay, so just be aware that all dimmers are not the same, and we want to keep them. You've got to understand what you're dimming before you can dim it. Here's a couple of examples of Emelec dimming drivers. So we've got the Dali. Dali is a commercial process, operates off a Dali bus, which a bus is 2 wires that continually bounces from one device to the other. We've got our 0 to 10 volt signal. Okay, that requires the ML2002 to actually operate, but it is not a resistive, but it's actually a 0 to 10 or a 1 to 10 volt percentage style dimmer. And we've got the Dali 2303, again it's another Dali dimmer. And in amongst all of that, we've also got the 1009 Fawi, which is our Wi-Fi RF dimmer as well. Okay, but that operates full LED strip, as does the 4-channel. The 0 to 10 can do LED strip or it can do lights, and the 2305 is designed for light fittings. Moving along to away from dimming for a second, life expectation is another area that is very, very confused. We have a lot of people out there that are struggling with understanding why my LED, you've said, will operate 100,000 hours. Well, that's now being changed. Okay, a lot of engineering and the Illumination Engineering Society of North America have actually stepped in and said, no, we need to work out how we can manage life expectancy. Now, when we look at LED lighting, it's not the LEDs that fail. It's the componentry that's attached to the LED that fails. So what do? So the easiest way is we do a workshop or a factory test. Once the light level drops to 70%, from 100% to 70%, that's the life expectancy. Okay, this is all done in-house under test conditions, and once it gets down, that's what we call L70. That is what we talk about when we look at the life expectation or the life expectancy of an LED light. It now means it reaches 70% of its initial output. That's when we gauge the lights. Now that can still be 30,000 hours, that still could be 40, 50,000 hours, it depends. But there's always an IES approved method for measuring all of this. So the whole process has now become a major process. It's called LM70, TM20 is the IES recommendation method. LM80 refers to the method for measuring the lumen depreciation of a solid state light source. All right, so before the advent of LM80, LED component manufacturers each reported lumen maintenance data. It wasn't controlled. Now it is. Now we have that L70. What does it look like? So this is what it looks like. We have time across the bottom, and once we get to that 70% mark, that's the life expectation of that light. So as you can see, we start at 100%. Now that time could be, 30,000 hours, 40,000 hours, right? Because it's about the depreciation in the light level. It's not about the failing of the equipment. So you may go through a couple of drivers because the LEDs are the ones that don't fail. It's the drivers that actually fail. Luminaire output and efficiency. Okay, this is a really good point. And when you're talking to customers and when you're talking to, you're trying to get somebody across the line, this is a really good thing to bring up to them. Lumens, okay, in simple terms, it's the light output. So, I'm looking at a light here. The lumen output is pretty good. If I was to have a dimmer, I could dim it down or I could ramp it up. But that's the lumen output. It's the visible light to the human eye, okay? The Luminaire efficiency is the ratio of light output emitted by the Luminaire to the light output emitted by its lamps. Not all light produced. So basically, if I was to pull this light apart, so you've got a diffuser on here. We've got a little bit of reflective material, but if I was to pull this light apart, the light that I would achieve here is different to the light I would achieve there. Now the reason for that is I have a piece of reflective material that sits in there, but I have heat losses. Even though they're LEDs, I still have heat losses. Even though I've got this big heat sink, I still have heat losses. So the light there is going to be higher lumen output than the light, when I put it all back together, that I achieve here. Okay? Because the diffuser, the heat losses and everything else will take effect and cause the light to be different at that level. And that's why there's two levels. Now here's another interesting factor. And I'll just pull my board over. As you can see, there's a little chart there, the little blue chart. Now it's not very clear, so just to make sure it is a bit clearer, when we look at the in your old workshops, warehouses, factories, we used to have what we called a high pressure sodium, mercury vapor or something like that. And what it was a big box of control gear with a big canopy, and it had a big bulb in the middle there, right? Now, they were great, and I've replaced thousands of them. But what happens is, they used to put out around the 10,000 lumens, all right? But what used to happen is the light used to go every which way, okay? Before it actually started to come down. So a test that was done, at this level here, we were only getting 4,000, right? 4,000 lumens at that level there, right? But we've got 10,000 starting up here. When you look at an LED light, and this was a 400 watt, right? When we looked at a 150 watt LED, right? All of our LED chips are here, right? The light that they send down is like this, right? So it's all heading in the right direction. So this is only 4,400 lumens here, but at this level here, we still achieved 4,000, right? Simply because each one of these is projecting at 120 degree, between 90 and 120 degree. This one here is just, it's a ball, and the light's going every which way before it comes down. It's relying on the reflectiveness of that canopy. If that canopy is full of dust, if that canopy is really dirty, this level here just keeps dropping. Whereas with the LED light, we started at 4,400, we've got 4,000, but everything's pointing down. So the chance of dust affecting the underneath there is minimal, because all of these are overshadowing each other because of the beam of the LED. That's a really important factor, and it's a really good drawing to go when you're talking to your customer, because it's really, really important when you look at it. We're going to talk now about efficacy, and it's not efficiency spelt incorrectly, but it's very, very similar to efficiency, right? It gives you a comparison of how many lumens each watt produces, and it's really important because, I mean, when we're looking for a quality solid light, like our Knox fittings or something like that, you want them to be able to shine up a whole yard, we're looking at, you know, the maximum possible lumens per watt. So, but when we're in here, what we're looking for is an average, a good lumens per watt. So somewhere in the 80 to 100 in here, in our lab, or outside, 100 plus. Or if I had a retail outlet, or if I had a motor dealership and I was trying to light up motor vehicles, I would be looking for that 100 plus lumens per watt, because I really and truly, I want to emphasize and I want to show the colors and things like that. So I want it as bright as possible. So when we look at that, it's measured it measures the net light output, okay, from the luminaire divided by the power into the system, accounting for the driver, optical and thermal losses. So we're just taking into consideration how much power does it take to run the light, and then comparing it to the output, and it's a bit of a formula, but it comes out with poor is 60 to 80 lumens per watt, average is 80 to 100 lumens per watt, and good is 100 plus lumens per watt. So depending on what we're looking for, they probably all have a place, but most lights sit in that 80 to 100, and sports field and outdoor lighting and all that will sit on that 100 plus. Okay, this is where we move into part 2. So the terminology that we spoke about previously is all about the designing and about what the fittings are and where they come from and so on. What we're going into now is the installation terminology. So we're taking that next step moving forward. One of the biggest things is, many years ago there was an issue, I was around at the time of halogen downlights. Halogen downlights were a 50 watt halogen downlight which could run anywhere up to 200 and odd degrees. They were frightfully hot, and if you put your hand just a metre below, you could feel the heat coming off the halogen light. And basically what was happening is they were setting fire to things. So with LED lights coming in, although albeit so slowly, they had to come up with some solutions. So they created a platform to reduce them down to 35 watts in the first instance. Then they designed cans to go over them to give them spacing away from the insulation and to make them all, you know, heat proof and things like this, and to generate the heat up into the ceiling rather than onto the timber beside it. You had to do all the spacings. But then they came up with a standard. Okay, they finally came up with a standard, and it's the Downlight Ratings Recessed Luminaire standard. Okay, so what we've got and what this means now with LED lighting is, because LED lights run so much cooler, we can now run hard up against timber beams. We can actually cover them with insulation and things like that. But we are only covering the light. We are not covering the driver. The driver must still sit on top of the insulation. So we've got the main ones are ICF and IC4. They are the highest level. Non-IC, that means it cannot be covered. It has to be gapped. You have to have your standard spacings as per your AS3000. All right, so as per the Australian standard. So you have to have those. All right, so the next one, CA135, that just means you have to get an insulation that has 135 degree fire rating, and it has to be stable at that 135 degrees. Okay, and it can only be close to or about the insulation, not over it. The next one is the CA80. It's okay, that's fairly good. IC, that one is getting better. You know, you can cover in a butt, yep. ICF and IC4 are the top, okay, because that means the insulation is rated stable at 90 degrees. We don't have to worry about it. It's reasonably common. You're not pulling something out like 135 degrees. You've got something that's reasonably common, and it works. But what we've got is we've got two examples up there, because when you look at a fitting, and this is a sample fitting, but normally they have a sticker on them and it says IC4 or ICF, or it might say IC, it might be CA80, it might have whatever it says on there, means it can either be covered, abutted, or it has to be spaced. So abutted means I can bring the insulation, can be placed up to the side of the fitting. Covered and abutted means I can go up beside it and up over the top of it. Now again, I say, we're only talking about this part. We are not talking about the driver. The driver must sit on top of the insulation at all times. All right, so that's a really important chart. Familiarise yourself with it, because it'll save you any issues or hiccups down the track, because if it's not ICF or IC4 and you cover it and the insulation is not correct, first of all, it could damage the LED. It could damage the light fitting. Second of all, you do still have that element of risk of fire or damage to the building. So just be mindful of that. It normally says it on the box, it says it directly on the fitting, so just be aware that it exists. IK rating is another, it's an impact rating. Okay, this has been in there, this has been around for many years, for over 20 years, but it was never really taken much notice of until the last 5 or 6 years when it started to appear more and more. The impact rating is, there's a series of tests, and then however the light comes out is the impact rating that it gets. And there's things from a swinging hammer to dropping a designated weight onto a light fitting, to dropping a light fitting, to all of these tests all indicate what the impact rating of that light. So for example, our Titans, our Noxes, our high bays are all IK10. Okay, that means they can take the maximum impact as per the chart that's possible. Okay, so when we look at our Nox fitting, we've actually run over it, we submerged it in the canal, and it still works. There is actually quite an interesting video on that, and also on our Nox there is also an interesting video with Tim Mobbs, the owner of Emelec. He shot it, it still worked, and the Nox was dropped off a bridge. The Titan was dropped off a bridge, thrown into a canal, driven over by a Pajero. So we have that, and that's on YouTube if you care to have a look. But it's all about the impact test. They are not the actual tests either, by the way. CRI. CRI is the Colour Rendering Index. Now, this is extremely important depending on your clientele. Okay, so when we talk about CRI, it's given from 0 to 100%. CRI will make my shirt, a poor CRI will make my shirt look grey. A good CRI will make it look blue, right? It's a blue. So we want a CRI of 85 to 90 is okay. If we can get 90 and over, that's what they class as a high CRI. Okay, so when you're doing a dress shop, for example, you want a high CRI because you want to show the true colours of all the apparel that's in and around the shelving. Right, if you're in a dealership, you want a high CRI. If you're in a nursing home or something and you're trying to create a little bit of effect or a relaxed atmosphere, you might want to go for a lower CRI, a warmer, cooler colour to just keep everybody relaxed. Okay, so CRI is really important, but it is very situational. You have to consider your situation before you actually go through and decide on what CRI I want. If it's an office building, you want clear, crisp light, but you may still only need a CRI of 85 to 90. All right, so you don't have to push it to that top level, but that's more about flicker free and glare and things like that. CCT, Correlated Colour Temperature. It's a really important one because over the years there's been so many different terms, and we've got most of the terms listed on that chart there. Cool white, daylight, neutral white, warm white, blue sky white. All of these over the years the terminology has changed. So the basic terms now are warm white, white and neutral white. So what white is 5,500 to 6,500 K. Kelvin is a temperature rating. It's a heat rating for a lamp, okay, but it's more about a heat colour, not actually a physical temperature. Okay, so white's 5.5 to 6.5. Neutral white is 4,000 to 4,500 Kelvin. Warm white is 3,000 to 3,500 Kelvin. Now, if you look to the right and you can see the chart, you can see a blue sky is 10,000 Kelvin, right? You can see that the window that most people operate in is between 2,700 and 7,000. All right, so that's where we sit. And most peak out at about 6.5, but the 2,700 can come back to about 2.5 with some fittings, depending on what the fitting is. But that's a really important chart. All right, power source, AC, DC, yes. I understand we're all electricians and things like that, but I still get this question. When we're looking at DC and DC lighting and things like that, they operate on LED lighting, sorry, they operate on DC, okay? But You can't just go and grab a car battery and throw it on there, because they operate at various voltages. And there's various formats. There's constant voltage, there's constant current. Okay? So when we look at LED strip, yes, it's 12 volts. And it's DC, but it's constant voltage. So the AC part is our house. It's where we live every day. You can have 415 volts, you can have 240 volt. DC, direct current, is basically what LED lighting operates off, but it operates off that through the appropriate driver. You don't just use a DC battery. We mentioned constant current and constant voltage before. This is really important because a lot of people don't actually get this, and I get a number of calls, looking after all the technical side of things, I get a number of calls daily as to go, you know, I need a driver. Okay, the first question you ask, is it constant current or constant voltage? What's it driving? So when they come to you and they say, I just need a driver, you go, well, is it constant current? What's it driving? Oh, it's driving a downlight. Okay, so that tells me pretty much that it's going to be constant current. All right. If you told me it's driving and it's operating LED strip, I'd say it's more going to be constant voltage. Okay, because LED strip relies on a constant voltage. These will operate on a voltage of anywhere from from 26 to 37, or from 30 to 65 volts DC, but they'll have a constant current. So that might be 1050 milliamps. It might be 680 milliamps. It doesn't matter, but it's constant. That's constant current. That's constant voltage. And there is a big difference. You cannot switch the drivers between the two. It will not work. Now, yes, I've got a ballast in there. Right, the reason I have a ballast in there is I still have electricians phoning up and asking for a ballast. A ballast for an LED light though. If they had a fluoro and they were looking for a ballast, no, we don't sell them, but we'd understand what they're asking for. But they're asking for a ballast because a ballast is a device that limits the current to a fluorescent to allow it to strike, and it's, you know, and basically allows a high voltage source for it to strike and then shuts it down straight away. That's a ballast. These operate off a driver, a power supply. A ballast is not a power supply at all. Once the arc is done, the ballast quickly reduces the voltage and regulates the electric current to produce a steady light output out of a fluoro. When you see a fluoro start to flicker, you know it's either the ballast or the starter that's starting to let go, or the tubes have let go. Okay, so ballast is something that's totally different. IP rating is very, very important. Okay, because this is something that has been around since I was an apprentice, which is many years ago. We won't discuss that. But the IP is ingress protection. The first number, which is the chart in yellow, and it's in your paperwork here as well. Okay, so the first number relates to dust. Is it dust tight, no ingress of dust, and also for fingers. Can I get my fingers in? Can I get, you know, a tool in there? Can I poke something in it? Okay. The second number relates to it's a water and the effect of it on water. Okay, so IP65 is very, very common. Okay, which means you can get a couple of jets of water and spray it down and do as you please. Okay, but the one thing I'll point out here as well is IP65 is for jets of water. IP68 is for being submerged and being submerged in water, but taking the pressure of that water around it. Now, if I was to take a device that is IP68 and put it up where I put an IP65 light, but all of a sudden put a jet of water, there's a good chance it will leak, because it's designed to take the pressure of being submerged, but not the pressure of jets of water. There's a big difference between the two. And that goes down the line. So you've got to pick the rating that is the most suitable for what you're doing. All right. If it was an LED strip, something like that, and they said, oh, it's IP68, I really wouldn't have any concerns with putting that and putting a jet of water, because it's going to be completely sealed. It's going to have resin, and the resin will be able to handle it as well. Okay, so let's move on. And then we've got the old IK rating chart just off to the right there as well.